Hi, welcome to another lecture on business mathematics. Today we are going to start a new topic, and this topic is probability. So if you listen to any news section, you probably going to hear about some numbers. Those numbers that you hear on the news, perhaps about the political election or weather forecasting and such, they connect to the area of probability and statistics. And today we are going to explain some of the basic facts here. We have to get used to some new terminology so that our problems can be stated clearly. And today I'm going to go over these mostly and explain what we mean by them. So first item is a trial or an experiment. What is meant by that? So imagine you have a coin and you flip the coin and then you record the kind of thing that would happen. Or perhaps you ask your friend to pick a number, like a single digit number. Or pick a card. Or you notice a family having 3 kids and you notice the birth order and the gender of kids. Or flipping 2 coins and such. These are all referred to as trials and experiments. When we conduct a trial, something is going to happen. That whatever happens, we refer to it as the outcome. So outcome of a flipping of a coin could be heads or tails. If you ask your friend to pick a number, perhaps he or she picks up 7 and so on. A set of all possible outcomes, that's referred to as that's referred to as sample space. Sample space is a set of all things that can happen. So if you flip a coin, it can land heads or tails. For short, H or T. That is referred to as the sample space. The standard notation is that we use curly bracket and list all the events in it and separate them by comma, and we don't duplicate our events inside that curly bracket, just one H, one T. For picking of a number, of course, we have all the digits from 0 through 9. They could be our sample space. For a deck of cards, that's a standard deck of cards without a joker to get started. Well, this is a standard thing that you play with it. So we have 4 suits and then we have ranks and face cards and so on. So that is the deck of cards we are referring to. By the way, this humongous number that you see here, that's total number of ways that you can actually rearrange a deck of cards. We'll come back to those type of issues later on. So when we are dealing with deck of cards, we have suits with diamonds, hearts, clubs, and spades. Diamonds and hearts, of course, red, and clubs and spades are black, and those are referred to as the colors. Then we have ranks from 1 through 10. Then we have Jack, Queen, and King. Those are referred to as the face cards. And the 1 sometimes referred to as ace, depending on the games that you play. It could be ranked above king or whatever. So when you pick a card, how would you notify that? Well, it all depends what is meant by the game that you play. But for example, you could say I picked 3 of diamonds. That could be referred to as an outcome. Now, how about kids in a family? Well, we have the first kid and the second kid and third kid and so on. And they could be boy or a girl. So we note the birth order, first, second, third, and then we note gender, boy or a girl. So a family with 3 kids, perhaps the first one is a boy and then a girl and then a girl, so that would be an outcome. Here's a list of all possible outcomes, so that we have boy, 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 girl, and so on, all the way through the list of all 8 possibilities, and we are going to come back to that. How do we arrange all of these possibilities, make sure we don't skip any possibility, and so on. We could think about more complicated experiments. So for example, you could flip 2 coins. In that case, for abbreviation, we just refer to possible outcomes: heads and heads, heads and tails, tails and heads, and tails and tails. And a possible outcome here, of course, would be that first I got heads, and then next I got tails, and so on. So that's a possible outcome of this list. Well, what do we do with this situation? These setups for our trial and experiments is going to allow us to talk about probability in a simple setting without getting bogged down into complicated situation like weather forecasting and so on, which is science all by itself. So next up, we want to talk about probabilities and what's the chance of a particular outcome, or what's the chance of a particular event. So an event is a subset of sample space. So all depends on what experiment you're running. Let's go through a simple one. Let's go back to this case of a family having 3 kids. Well, there are families that have 2 boys. By that we mean exactly 2 boys. So say exactly 2 boys. What are the possibilities? Perhaps first one was a boy, and second one was a boy, and the third one was a girl, or it was a boy, girl, boy, or the first one was a girl and the next 2 were boys. So these are 3 possible situations out of all 8 of them where a family could end up with having exactly 2 boys. So what if we say 2 or more, or 2 or 3 boys? Well, into the listing that we had before, we are adding the case of 3 boys as well, and now we have 4 situations in which the family has 2 or 3 boys in their family. Now next we are going to come up to the issue of probability. So when we are dealing with this kind of a situation in these experiments, we want to know how likely is it for something or another thing to happen. We have 2 general broad situations. One is the classical problems like this coin tossing or picking up a card and so on. These are easier to talk about and imagine and describe. We have also a situation which, where the numbers are experimental, for example weather forecasting and so on, which we are going to rarely talk about them at this stage. We want to talk about the probability of something. So if we are talking about families having 3 kids, what's the probability of all kids being boys? What's the probability of all kids being girls? What's the probability of having exactly 1 girl in a family? And so on. We want to assign a probability in the 2 ways we can go about this. One is to go and actually observe the situation in an experimental way and come up with a answer about it, and the other one is by conducting a thought experiment and base our answers on that one. We are going to need a notation how we are going to talk about probability. So we are going to use the letter P as a shorthand for probability, and we always talk about probability of something. So in this notation there's always a of here, and then we have a certain event in our mind. So event could be again whatever we are describing, a particular subset of our sample space. In the case of cards, fair dice, fair coin, and so on, we use the equal likelihood model. Equal likelihood model means all these cases individually are equally likely, and the way we come across our probability is to count the number of outcomes in the event X and divide it by the number of outcomes in the sample space. So what does that mean? So for example, what's the probability of having exactly two boys? Exactly two boys, there are three possibilities. Out of all 8 of them, the probability of having two boys, exactly two boys, will be 3 divided by 8. That's a chance of having exactly two boys. Similarly, the chance of having 2 or 3 boys, again, we look at the sample space. We see there are 8 possibilities here. They are all equally likely. 2 or 3 boys. There are 4 out of these 8 that are matching our criteria, that are matching our event. 4 out of 8, which is 50%, that becomes the probability of that event. So this probability always a number between 0 and 1. The numerator is always less than the denominators, at most is equal to it, and that is the reason that the probability is always between 0 and 1. So of course, if I ask what's the chance of having 4 boys in a family with 3 kids, of course probability of that will be 0. So when is it the probability 1? Say what's the chance that the family will have either boys or girls? Well, that's all the chances that we have here, and all families will fall into one of these categories. In that case, probability will be 1. In experimental situations, we have a set of data presented to us, and based on that data, we look at the data and decide how many times our particular event happens, divided by number of times the experiment was conducted, and make it the decision based on that. Now let's go ahead and do some simple experiments. Here I'm going to make use of some demos that we have here. So for example, the case of coin flipping. I'm going to put a link to this, or you can just copy that from your screen. You decide first how many coins you want to have. You can have 1 coin, or you can have up to 8 coins here in this little app. You can play with all those cases. Let's take 1 coin. Well, you flip a coin. Here you flip it. Well, it came heads. The software counts how many heads showed up. So far, 1 head shows up once. You flip again. The tail counts as 0 heads. So it showed up once. I flip again. By now we had 2 cases where heads showed up. 1 case where tails showed up. Toss it again. By now it became 2 and 2, and then you can continue this, and you can flip the coin and go on. After a while you get tired of clicking, so if you want to do delegate it to the software to do this thing 10 times, and then for each case it tallies for you how many heads showed up. So here I add a 10 if I want another 10, another 10, another 10, and so on. Well, We assume this is a so-called fair coin, and the probability of getting heads is denoted here, so it's 0.5. If you want to rig the game one way or another, you can play with this slider, make the coin to be heavier on one side than the other one. So we are going to come to that issue later on. For now, uh, all of them are going to be equally likely. Of course, you can start from scratch. You can always press the reset button and do like that. Well, uh, that is one way of handling this. Sometimes maybe you want to have more coins, make the problem more interesting. Now, we start with 3 coins and then we flip all of them. Take 3 coins, throw it onto the floor. So what could happen? In each round, well, we have to decide what is it that we are counting. Let's just go ahead and do a simple thing of counting how many heads shows up. Well, like this, it could be that no heads are there at all. It could be that one of them turns out heads. It could be two of them turns out heads. It could be 3 of them turns out heads. We don't care about the order in which they show up. So one flip means all 3 of them were flipped. All 3 coins, we take them and throw up in the air. We got 2 heads. So by now we had one case where two heads showed up. Let's do another one. Again, the same thing, but the different arrangement. Here we had, out of the 3 coins, one of them was heads, and that is what is counting here. Let's do another one. Again, only one head showed up. Here is all of them became heads. So the software records for us that there has been one case in which 3 heads showed up in one throw. And so on. We can go ahead and repeat this game over and over again. To do it quickly, like do it 10 times and record all of that. So we see that in 9 cases there was a single head. In 1 case there were all tails. In 4 cases there were 2 heads. In 1 case there were all heads. And we can repeat this thing again and again. You see a particular curve showing up. Later on we are going to talk about this so-called normal distribution or bell curve. That's very famous. We are going to do that. Sometimes perhaps you want to have more coins. Maybe I start with, say, 6 coins here, and it resets it for me. And let's just do it quickly. I'm throwing all of them at the same time and doing it 10 times and record it, and you notice that this becomes close to that famous bell-shaped distribution that you see in many areas of sciences wherever they handle data, and this curve does show up. Okay, so this is one of these type of experiments we can play. Here computers helping us to tabulate what comes out. We can approach the problem theoretically by actually arriving at what will happen in the long run, and the other one is just by doing an experiment, which means just literally flipping these coins more and more often. As you flip more, it's going to change the scale in order to be able to show all of them here. So this was one such experiment you could conduct. Let's go to another experiment. This is perhaps more familiar to you from perhaps backgammon or some other games you play. We have dice to throw, and we can decide how many dice we want, like let's see, well, just 3 dice or 2 or of course 1. Well, when you throw a dice, what do you notice? In number of dots Let's roll a die in this case. Well, I got a 2. Now I roll it again. I just click here. I got a 3, and I got a 6 now. So you see 6 dots, and I got. So as we continue this, if this is a fair die, uh, it would mean all of these outcomes are equally likely. They are as likely as each other. Each of them is going to show up about 1/6 of the total. So I have 20. I have rolled this thing 25 times. 1/6 of that is 4 and something. So more often than not, we get 4. So we got 4 2s, 4 3s, 4 4s, and because, well, this is a random event, it so has happened that in this experiment we had we had 8 cases where 5 showed up, and 3 cases where 6 showed up, and so on. Well, you can throw it 10 times to be fast. You can throw it 100 times and the computer is going to tabulate it for you. You notice there is some discrepancy because after all this is a random event. As you increase the number of rolls, you see that it levels off. So here we see that we have thrown this thing 10,135 times. Is cumulative. You see that the number of times things come out, they become the same. They are not identical, but they're close to each other. The maximum we see here 1719, and what is the smallest one, 1654. So there is a gap of about 65 from here to there, but they kind of became level off. To make the matter more interesting, make problems a lot more challenging, we can increase the number of dice that we have, 2 or 3. Well, the case of 2 dice, as I said, you play with it quite often, well, say games like backgammon and so on. So when you roll this thing, what can happen? Well, you can have 1 and 1, you can have 1 and 2, 1 and 3, and then so on through 1 and 6. You can have 2 and 1, 2 and 2, 2 and so on through 2 and 6, 3 and 1 through 3 and 6, 4 and 1 through 4 and 6, 5 1 through 5 6, and then 6 1 through 6 6. So there are 36 things that can happen. Perhaps imagine one of them is red, another one die is green, so that you know who turned out to be what number. 36 possibilities. So what are you going to do? Well, you have to define a certain kind of a game. Standard game is to add up how many dots you got. So here you say I got 2. I roll that dice. Well, I got a 4 now. 3 plus 1 is a 4. By now I have one case in which I got a 4. Let's throw this thing again. 5 and 4 is total 9. I got one case where I got 9. I keep doing this thing. What's the minimum I can get? Minimum I can get is a 2. 1 and a 1. What's the maximum I can get? The maximum is a 12. 6 and a 6. So I can keep throwing this dice and add these things and see what happens. After a while I want to go faster than this, so maybe I throw this thing 10 times and record all of them. So here, let's see, is it responding? You see that the computer is throwing the dice for me and counting. So by now I have 3 cases in which the sum was 2, 5 cases where the sum was 3, and so on. Now the question comes up, as we keep doing this thing, what's going to happen? So that's going to be one of the interesting problems coming up. Here we can do it experimentally. If I do it 10,000 times, here I do it 10,000 times, you see we are going to get this particular distribution. and we are going to talk about the curve that we are getting. Uh, yeah, if you want to do it one more time, like 10,000 more times here, 10,000 more times, and so on, you see the most common thing to get is 7. We can kind of get a sense why is that. 7, I can get it out of 601 or 502 or 403 or 304 and 205 and 1 and a 6. I have 6 different cases that leads to 7. But how do I get a 2? The only way to get a 2 is to get 1 and a 1. So that's less likely than getting a 7. What's the maximum? Maximum is 12. Why does it happen so few times? Because the only way to get a 12 is to get a 6 and a 6. So that is about as likely as getting a 2 because there are very few cases where those numbers show up, as opposed to what? Well, 7 is much more likely than anything else because there are so many cases that leads to a 7. We said anything from 1 and a 6 to all the way to 6 and a 1. There are 6 cases where this happens. So as you notice, this is 6 times more likely than this. This happened 500 and so many times. This happened about 3,000 times. This is 6 times bigger than that one. So those are the things that we have in store for us. We want to study all these cases and assign probabilities to them. Again, we are looking at these cases of these games and simple experiments in order to be able to actually carry it out. Like you can take actually a coin and do this thing all by yourself, and or write it down and such, as opposed to complicated experiments that might not be easy to carry out. Okay, so next time we are going to solve a few more problems and talk about these various cases. So again, going back to what we learned today, we have trial or experiment, like flipping a coin, sample space, set of all things that could happen. We make a recording of it, curly bracket, separate the cases with a comma. Outcome, as the word implies, of what could happen in a single run of the experiment, that is referred to as an outcome. Then we have a probability. We have a classical cases, we have experimental cases. Classical cases are with fixed essential probabilities and typically like equally likely scenario in which we can do the problem by simple counting. We count how many times certain thing happens, we count how many total number of possibilities there are, and the ratio is going to give us the probability. So I hope you read your text, and then in next run we are going to do some experimentation and problems. Until then, good luck and God bless.